In this talk, I'm going to present a novel algorithm for obliviously merging two sorted lists using order of n log n secure operations. So the setup is that we have two sorted lists, the blue list and the green list, and we want to merge them into a single sorted whole. And now, if we weren't interested in data obliviousness, it's straightforward to merge these two lists in order of n time. But if we require the merge algorithm to be data oblivious, that problem becomes much more challenging. Now, roughly, an algorithm is data oblivious if its control flow does not depend on the input data. And this can happen if the algorithm is completely deterministic and data independent, or if the algorithm is randomized and data independent. We can also achieve data obliviousness by declassifying certain data during the computation and allowing the further control flow to depend on the public data as well as on the previously declassified data. But if we do this, we still need to ensure that the distribution of all the declassified data, along with the point at which it was declassified, is independent of the input data. And this is the type of data obliviousness that's achieved by most cryptographic constructions like sorting algorithms and oblivious RAM protocols. Now, before we dive into our new merge protocol, let's look at some applications of secure merging. One application is in private set intersection, and in particular in the sort, compare, shuffle paradigm. So in this situation, we have two lists, A and B, and we want to find their intersection. And to do this, we concatenate the two lists, and then we sort the unified list. And then we compare adjacent elements to see if they're equal. And because the entire list is sorted, we're guaranteed that any duplicate elements will be adjacent to each other. Then we just zero out all of the elements that weren't equal to its neighbor. And this list is the intersection of the blue and green lists. And although there are dozens of other private set intersection protocols, one nice thing about the sort, compare, shuffle paradigm is that it's generic and composable. It's generic in the sense that it can be implemented using almost any secure computation framework, and it's composable, meaning that it can work on secret shares and return a secret sharing of the intersection. By contrast, a lot of the fastest private set intersection protocols return the intersection in the clear and thus can't be composed with other larger secure multiparty computations. And designing composable private set intersection protocols is critical for designing bigger systems for securely computing on databases. And secure multiparty computation systems like SMSQL or Conclave or Senate that privately compute on databases rely heavily on secure database joins, which in turn rely on secure merge protocols and secure private set intersection. And so improvements in the underlying secure merge protocols lead to direct improvements in these secure multiparty computation platforms for computing database joins. Now, merging two lists is certainly no harder than sorting the two lists together. And sorting networks like the Batcher sort or the AKS sorting network provide a deterministic data-independent method for sorting two lists. Thus, these sorting networks also provide a method for merging two lists obliviously. And although the AKS sorting network is asymptotically superior to Batcher's, the hidden constants in the big O notation are so large that it's essentially useless in practice. On the other hand, Batcher's sorting network, which can sort n items using n log squared n comparisons, is fairly simple. On the other hand, Batcher's sorting network can sort n items using n log squared n comparisons, and it's fairly simple and is thus widely implemented in secure multiparty computation platforms like EMP, oblivc, and ABY. An alternative method for obliviously sorting a list is the shuffle-then-sort paradigm. And the shuffle-then-sort paradigm works by obliviously shuffling the data and then performing a standard sorting procedure where the data movement is in the clear. And the oblivious shuffle ensures that the data movements performed by the standard sorting procedure are actually independent of the underlying data. And the shuffle-then-sort paradigm can be used with a variety of standard sorting algorithms like radix sort or quicksort. And if both the shuffle and the sorting procedure are order of n log n, then the oblivious sorting procedure is also order of n log n, which is asymptotically superior to using Batcher's sorting network and is practically superior to using the AKS sorting network, because the constants in this case are fairly small. But in order to use the shuffle then sort paradigm, you first need a data-oblivious shuffle. And one method for obtaining a data-oblivious shuffle is to use the Waxman permutation network, which can shuffle n elements using n log n controlled swap gates. And this is fairly efficient in both theory and practice, and we've implemented it in EMP Toolkit. Alternatively, oblivious RAM protocols can be used to build oblivious shuffles, but although these are very efficient asymptotically, they're not nearly as efficient as Waxman shuffles in practice. In the multiparty setting, for example, when there are 3 parties that hold secret shares of a list V, we can actually obliviously shuffle very efficiently. And to do this, player 0 reshares his share to players 1 and 2, and then players 1 and 2 together choose a permutation, sigma 1, 2, and then they use the linearity of the secret sharing scheme to reconstruct a 2-party sharing of this original secret V, and then they permute the shares of V using this permutation, which is public to players 1 and 2. Then they reshare these permuted shares back to player 0. And at this point, the 3 players hold shares of the vector V that's permuted by the permutation that's known to players 1 and 2. And then if players 0 and 2 repeat this procedure, and players 0 and 1 repeat this procedure, the 3 players end up with a 3-party secret sharing of the initial vector V permuted under 3 permutations, and each player doesn't know at least one of these permutations. But this protocol is extremely efficient in practice because all 3 permutations are done in the clear by 2 parties. So this gives a 3-party shuffle protocol with linear communication that's compatible with essentially any MPC framework. And it turns out you can adapt this idea to the 2-party setting using additively homomorphic encryption. So in the 2-party setting, if players 0 and 1 hold additive shares of a vector V, then player 0 can send the encryption of his shares to player 1, and then player 1 can choose a permutation and permute player 1's share vector as well as the encrypted share vector. And after player 1 has permuted these 2 vectors using the same permutation, then player 1 re-randomizes his shares, as well as re-randomizing the encrypted shares of player 0. And this is where player 1 has to use the fact that the encryption scheme is additively homomorphic. And after re-randomizing these shares, player 1 sends the permuted, re-randomized encrypted shares back to player 0, who can then decrypt them. And at this point, the players hold a sharing of the secret vector V permuted under a permutation known to player 1. So then they just repeat this procedure, swapping the roles of player 0 and 1. Okay, so let's look where that puts us for existing oblivious merge protocols. So to recap, Batcher's sorting network provides an order of n log squared n oblivious sort. The AKS sorting network provides an order of n log n oblivious sort, but the constants are terrible. And the shuffle then sort paradigm provides an order of n log n oblivious sort that's actually practical. But if we didn't care about obliviousness, we could merge in linear time. So can we do an oblivious merge in linear time? Well, it turns out that in the 3-party setting, there is a linear communication secure merge protocol, but no similar result is known in the 2-party setting. And some lower bounds on oblivious merging are known. For example, when one list is small, then Batcher's merging network is optimal if you require deterministic data independence. But the main contribution of this work is to give a novel 2-party oblivious merge protocol that only requires order of n log log n communication, which beats the order of n log n communication, which was the previous best bound in the 2-party setting. So here's how our two-party secure merge algorithm works. We have the blue elements, which are sorted and provided by player 0, and the green elements that are sorted and provided by player 1. And you want to think about all these elements as being secret shared between the two players. And then we're going to take these elements and divide them into blocks of width W. And we're going to call the first element in each block a pivot. And then we're going to sort the blocks by their pivot. And we're going to store these pivots because we'll need them in a later step. So how do we actually sort these blocks? If we use a traditional sorting algorithm like a sorting network, this will actually take n log n time. But with an oblivious shuffle protocol, we can sort these blocks very efficiently. And the idea is we'll tag each pivot with a random ID, and then we'll tag each block with the identifier of its pivot. Now remember, the blocks are of width W, so they're n over W blocks, which means they're n over W pivots. And we'll sort these n over W pivots using an efficient oblivious sorting algorithm. And then we'll shuffle each of the blocks, and then we'll reveal both the pivot IDs of the sorted pivots and the block IDs. But after that, we can match the block IDs to their pivot ID, and we can move the secret shared block to its appropriate pivot, and we can do that data movement in the clear, because that data movement is independent of the underlying data. And after this sorting procedure, we have that the elements within a block are sorted, and we can prove that the number of elements that are somehow far from their correct position in the truly sorted list is not very large. Because it is possible that some of the elements are out of place. For example, this blue element maybe belongs after this section of two blocks of green elements. But essentially, this is the only way an element can be far out of place. For example, if a blue element is going to be very far out of place, it needs to jump essentially across a few blocks of green elements, and there aren't that many ways that that can happen. And we prove this rigorously, that there aren't too many elements that can be very far out of place, or what we call stray. And this whole sorting by blocks procedure takes order of n over w log n over w plus n secure operations. And we're going to set the block size w to be about order of log squared n. And the next step is to now find these elements that are stray or very far out of place. And to do this, we'll sort by sliding windows of t blocks, and we'll tag an element as stray if during this sorting procedure it moves by more than delta t blocks. So first we'll sort the first t blocks, and then we'll sort the next t blocks, and the next, and so on. And we'll keep track of how far each element moves in this sorting procedure, and elements that move too far in the sorting procedure will be tagged as stray. And now there are n over w blocks, and each block is of size w, and so the total amount of communication required to do this step is n over w times the communication required to sort a block of size w. And this will be order of n log n if we assume that the block size w is order of log square n, and sorting takes n log n time. So now that we've sorted sliding windows of size t, and we've tagged some items as stray, we want to now remove these strays and put them into another list. And so we imagine, say, that these two blue blocks were labeled as stray, and we put them into a new list. And to ensure data obliviousness, this list needs to be padded up to a specific size, because the number of strays might actually leak some data. So this list of strays will always be padded up to a fixed size. And we can get a concrete bound on the number of strays, so we know that this list will never overflow. And extracting these strays can be done in linear time, just with a linear pass over the entire list. Now there are some gaps in the list where the strays were removed from the list, but we can remove these gaps using a stable compaction algorithm. Now, there are several compaction algorithms from the oblivious RAM literature that run in linear time, but these are not stable, meaning that they might rearrange some of the elements that were not dummy elements. On the other hand, if we have a linear communication oblivious shuffle, then linear communication's oblivious stable compaction is actually very easy, and so we use that. And this compaction step also requires linear time and communication. And our next step is to reinsert the strays back into the original list into a position close to where they need to be. And so here's how we're going to handle that. We take the list of sorted pivots that we saved from step 1, and now this lower list of strays and dummies. Then we sort the pivots and the strays together, and we can do this efficiently because there aren't too many pivots and there aren't too many strays, so we can do this using an n log n sorting algorithm. And then with a linear pass over this list, we'll tag each stray with the identifier of the pivot that immediately preceded it. And this procedure will take order of b plus n over w, where b is the maximum number of strays. So next, we have to actually reinsert the strays into this list. So we have this list with these white gaps where we removed strays. And we have the list of pivots and strays sorted together. So we're going to create a bunch of empty spots that immediately follow each of the pivots. So we can think of these white boxes as empty slots that are going to be inserted right after each pivot. And we're going to insert the same number of slots after each pivot because we need to insert the same number for data obliviousness. And the next step will be to actually put the strays in the correct slots. And since the pivots and strays are sorted together, we actually can see this mapping that maps the pivots back to the slots that correspond to that pivot in the full list. And so using this mapping, we then map the pivots as well as the dummies back into the slots that correspond to the correct pivot. Now at this point, most of the slots will be empty, and some of the slots will be filled by dummy elements, but all of the strays will be near the correct pivot. And so then we're going to insert this block, in this example, this block of 3 slots right after each of the pivots in the full list. And this whole thing can be done in a linear pass, and so it takes linear time. Then next, we run a stable compaction again to remove all of the empty elements from the slots that we inserted. And this puts all of the empty elements at the end, and this takes linear time, as we mentioned before. And now that each stray has been inserted near its correct pivot, we can get each stray to the exact correct location just by sorting sliding windows like we did before. So we sort a sliding window of a few blocks, and then the next set of blocks, and the next set of blocks, and so on until the whole list is sorted. And as before, this takes order of n log n time if the block size is polylogarithmic. So putting this all together, we have a 2-party secure merge protocol that only requires order of n log n communication, whereas the best previous 2-party secure merges required order of n log n communication. Now, our construction requires a linear communication shuffle, and currently that construction requires additively homomorphic encryption. But the rest of the protocol uses only generic secure computation, basically equality tests and comparisons. Thanks.